Hey, we are in lesson 10, normal distributions. In this first exercise, we're going to review what is meant by normal distribution. We're also going to learn how to calculate z-scores, which is pretty cool. All right, so consider the following data distributions. In the previous lesson, you distinguished between distributions that were approximately normal and those that were not. For each of the following distributions, indicate if it is approximately normal, skewed, or neither, and explain your choice. Okay, I'm going to get a little bit of a thicker pen, just because I can draw sort of the curve over the graph a little bit better. So if we look, okay, I'm just trying to hit each tip, and this looks pretty normal. This is approximate. I would say this right here is approximately normal. I would say it is symmetrical or mound-shaped. If we look at graph B, again, grab a marker, just draw a curve over it. For B, I would say the exact same answer as A. Okay, it's approximately normal, it's approximately symmetric, and mound shape. Okay, those are pretty apparent. Okay, letter C, not quite as apparent. So if I draw this curve, it goes up and then down. Okay, here I would definitely say not symmetric. Therefore, not. That was messy. Not approximately normal. Okay, we definitely have skewed to the right. We say most of our data is in the beginning. Can't spell beginning, or left, and then tapers. Okay, this right here is called our tail. Here once again, if I just draw over, I would say, just like A and B, oops, I'm green. I'd say it's approximately normal. It's symmetric and mound-shaped. Okay, I'm not sure what's going on here with this next one. Like, it looks like a box, right? So this distribution is not approximately normal. Forgot the R. It is symmetric, but not mound shape. Right? It's not skewed. It does not have a tail. Okay, these are all things I'm just looking at the shape and noticing. I would describe it as uniform. I can't think of anything else to describe it as, right? Okay, but we can definitely say not approximately normal. It is symmetric. It's not mound. It's not skewed. There's no tail. It's very uniform. Just to be clear, this right here is a picture of a normal distribution. Okay, a normal distribution that has a particular symmetric mound shape. Okay, shown below. That's sort of our model for what we're doing. All right, before we move on, let's talk a little bit about z-scores, why they exist. Okay, suppose you took a math test and a Spanish test. The mean score for both was 80. You got an 86 in math and a 90 in Spanish. Did you necessarily do better in Spanish relative to your fellow students? Did you necessarily do better in Spanish relative to your fellow students? Okay, let's talk about it. No. All right, for example, suppose the standard deviation of the math scores was 4, and the standard deviation for the Spanish was 8. Then the score of 86 in math is 1.5 standard deviations above the mean. And my score of Spanish is 1.25 standard deviations above the mean. So that means that relative to other students, I did better in math. It's one of the great things about statistics is it really dissects the data. Okay, it really makes sure that the data supports claims, right? All right, so what's really going on here is the z-score for math is 1.5, and the z-score for Spanish is 1.25. Okay, that's what we're working on today. Also, I'll point out that negative z-scores indicate values below the mean. In our example here, we talked about above the mean, right? All right, moving on. Okay, exercise 2. When calculating probabilities associated with normal distributions, z-scores are used. A z-score for a particular value measures the number of standard deviations away from the mean, A positive z-score corresponds to a value that is above the mean. A negative z-score corresponds to a value below the mean. The letter z is used to represent a variable that has a standard normal distribution where the mean is 0 and the standard deviation is 1. This distribution was used to define a z-score. A z-score is calculated by, given right here. All right, let's try one. The prices of the printers in a store have a mean of $240 and a standard deviation of $50. The printer that you eventually choose costs $340. What is the z-score for the price of your printer? So we've got our value, let me change colors here, of $340 minus the mean, which is 240, divided by the standard deviation. which the problem says is 50. So my z-score is 2. How many standard deviations above the mean was the price of your printer? The price of my printer was 2 standard deviations above the mean price. Ashish's height is 63 inches. The mean height for boys at his school is 68.1 inches. And the standard deviation of the boy's height is 2.8 inches. What is the z-score for Ashish's height? So I have z equals Ashish's height, which is 63, minus the mean, 68.1, divided by the standard deviation, divided by 2.8. This gives me approximately negative 1.82, because we're going to the nearest hundredth. Okay, we're negative, right? So the meaning of this value is Ashish's height is 1.82 standard deviations below the mean. AGI, for boys at his school. Goodness. Cool. Explain how a z-score is useful in describing data. A z-score is useful in describing how data for a particular point, how far data from a particular point is from the mean. So it's useful in describing how far a particular point is from the mean. So very useful. All right, now we're going to go through using z-scores and a graphing calculator to find normal probabilities. Okay, there's some new information we're going to get through this example, and we're going to use our graphing calculator to graph some things and to find some data. So a swimmer named Amy specializes in the 50-meter backstroke. In competition, her mean time for the event is 39.7 seconds. The standard deviation of her times is 2.3 seconds. Assume that Amy's times are approximately normally distributed. So estimate, I hate estimating, but we're going to learn how. The probability that Amy's time is between 37 and 44 seconds. So let's go ahead and put her mean time here. And we know a standard deviation in this direction. I'm going to subtract 2.3 and get 37.4. If I subtract 2.3 again, let's see, 35.1, add 2.3, I get 40, solid 42, and if I add 2.3 again, I get 44.3. So really, I've got one standard deviation, another one, and another one. I know I'm 0.3 seconds off, but, if I've got my curve, and I go out here and out here, this is the mean. I'm going 2 standard deviations this way, 2 standard deviations that way. It's going to cover almost all of my data. It really will. I know I'm over a little bit here and under quite a bit here, but we can assume, being so close, that we can be about 0.9, the probability of 0.9 that Amy's time is going to be between these two, or 90%. Okay, this is an estimate, and it's approximation, which I know we love. Using z-scores in a graphing calculator and rounding your answers to nearest thousandth, find the probability that Amy's time in her next race is between 37 and 44 seconds. All All right, so let's calculate some z-scores. First, let's look at the 44. So we have z equals 44 minus the mean over standard deviation, and we get 1.870. And let's do for 37. So 37 minus the mean over the standard deviation, and we get negative 1.174. Sorry, my pen's all messed up. Cool. All right, we have these two z-scores. I need to go to the next page to continue to show you how to do this. We're going to calculate our standard error probability, okay, because I don't like estimating. So we're not going to do this. Go to the next page and we'll do it. We're going to calculate probability. Get your calculators out. Okay, here's an awesome calculator. A little bit small. Let me see if I can make that bigger. Cool, I can. All right, what I need you guys to do is, make it a different color. We're going to first make sure our stat wizard is off. So hit the mode button. You're just going to have to follow along verbally. Arrow down. And I'm looking for stat wizards. And turn that off. Okay, if your calculator doesn't do this, I should have a calculator on my marker tray, my dry erase board, or we can do it tomorrow, but you're going to be happier if you can figure this out today. So after you do that, you turn stat wizards off. You're going to go back here and go second quit. Cool. Next, we are going to hit the, sorry, I have a tickle in my throat today. Second DISTR, so second, and it's right here, the button, and you're going to select number 2, which is normal CDF. Right, let me double check that. Normal, yep, normal CDF, parentheses. So go ahead and select number 2. And it should look like, your screen should now look like this. Right here, it should say normal CDF, parentheses. You're going to want to type in your z-scores you just calculated. So I'm going to type in negative 1.174, comma, 1.870, comma, negative 1.174, comma. Here's the comma button right there. And 1.870, close my parentheses. And I get an answer of 0.849. Okay, that right there is my probability that Amy's time is between 37 and 44 seconds. Cool? All right. Estimate the probability that Amy's time is more than 45 seconds. Again, this is an estimate. When it says estimate, that means we're not using our calculators. Blah. But we're going to try it. So 45 seconds is going to be more than 2 standard deviations away from the mean. Okay, so your probability, that's going to be pretty small. I don't know what kind of number to throw at small. So I look at the answer key and we estimate about 0.03 or 3%. Okay, so pretty small. Using z-scores and a graphing calculator, let's calculate it ourselves. So the z-score for 45 is 45 minus the mean over the standard deviation, and that gives us 2.304. Okay, now this problem's asking us to find the probability that Amy's time in her next race is more than 45 seconds. So this right here is actually going to be the low end of our limit when we do our normal CDF. normal, C, D, F. Our high end of our limit is a large number, okay? And practically speaking, we're going to use 999 for an upper bound. And that's just something we'll do every time when we don't have an upper bound. Okay, so go ahead and do the second DISTR, find 2 normal CDF, and plug this into it. Okay, I'm going to go ahead and do that now. 2.304, comma, 999. And I get a probability of 0.0106. Okay, that's itty bitty, right? But that's what we're going to do. Okay? I see a mistake here. Okay, thousandth. So this should be a 1. Okay, 0.011. Okay, I'm going to draw a picture on the next page. If you go back up to letter B, okay, I've got a normal curve with my mean in the middle, 37 to 44. Okay, I'm just drawing a picture to represent what we just did, right? So this right here gives me a z-score of 1.870, and this one is a z-score of negative 1.174. We're trying to find the probability that her swim score is going to be in between those two values. And then if I look at D, same normal curve. I know that's not beautiful, but we're trying to find the probability that her swim score is above 45, which is this itty bitty little piece right there. Okay, super small. So our probability is going to be much less. Our probability is pretty big here. Our probability is pretty small here. What is the probability that Amy's time would be at least 45 seconds? So that was just, letter D was more than 45 seconds. I don't want to do that. So if I look at letter E, since Amy's times, you know, it's on a normal curve. That's terrible. I'm so sorry. A little bit better. Since Amy's times have a continuous distribution, the probability of more than 45 seconds and the probability of at least 45 seconds are the same. So more than 45 seconds is going to be this little piece, and at least 45 seconds, that's got the same meaning. So our answer is going to be the same as part D, about 0.011. So that's just a different way to say the problem, a different way to state the problem. Okay, F. Using z-scores in a graphing calculator, rounding your answers to the nearest thousandth, find the probability that her next race is less than 36 seconds. So our z-score is going to be 36 minus 39.7 over 2.3, which gives us negative 1.609. Okay, if I do my normal CDF, this right here is going to be my upper bound, so I want to put a negative big number into my lower boundary. And if I calculate that, I get a probability of about 0.054. And if we, I don't know why I keep doing that, if we look at our curve, okay, that would be 36 seconds. We're trying to find this itty bitty little lower piece right there. Cool. All right, moving on. The distribution of lifetimes of a particular brand of car tires has a mean of 51,200 miles and a standard deviation of 8,200 miles. Assuming that the distribution of lifetimes is approximately normal, distributed, and rounding your answers to the nearest thousandths, find the probability of each event. Okay, so let's look at it. I need to calculate some z-scores. If I look at my curve, I've got this a mean of 51,200. And I'm trying to find between 55,000 and 65,000 miles. I'm trying to find this piece right here. So we can find our z-score for the low end. 55,000 minus the mean over the standard deviation. Sorry, that's our first z-score. Then our second z-score for the upper. I just didn't think you guys wanted to listen to me type on my calculator. Right there are my two z-scores. So I'm going to find my probability using the normal CDF. My low end and my high end. Can't type. Can't write. I can type some days. We get a probability of 0.275. Okay, how about a randomly selected tire lasts less than 48,000? So right here, we have 48,000, and we're trying to find this one. So that means we're going to use the negative 999 in our normal CDF. So let's find our z-score for 48,000. Excuse me. It should be negative, right? 51,200 all over 8,200. I get a z-score of negative 0.390. I'm going to put that into my normal CDF. So second distribution, negative 999, comma, negative 0.390, close parentheses. I get a probability of 0.348. A randomly selected tire lasts at least 41,000 miles. So we're hit 41,000 and we want this whole piece. Ooh. All right. So my z-score is the value minus the mean over the standard deviation. So my z-score was negative 1.244. If I plug it into my normal CDF in my calculator, I get a probability of 0.893. Notice my upper boundary is a big number, right? My lower boundary is my z-score. Explain the meaning of the probability you found in A, part 3. So if a large number of tires of this brand were to be randomly selected, okay, a large number of tires for this brand were to be randomly selected, you would expect about 89.3% of them should last more than 41,000 miles. Okay, moving on. Exercise 4. Think again about the brand of tires described in exercise 3. What is the probability that a lifetime of randomly selected tires is within 10,000 miles of the mean lifetime for the tires of this brand? Okay, so if I look at my curve, my mean is 51,200. What's the probability that 41,200, my curve isn't very symmetrical, is it? 61,200. Okay, what's the probability that the lifetime of a randomly selected tire is within 10,000 miles of the mean? So I need two z-scores. I'm going to calculate those real quick. So I have my two z-scores. I'm going to put it into my calculator. Neg the lower boundary, 220, and the upper boundary. And I get a probability of 0.777. Okay, it's a pretty good probability, right? All right, example 2, using table of standard normal curve areas. I did not provide this for you, so let me talk through this example, but we're not going to finish these next few slides. The standard normal distribution is the normal distribution with a mean of 0 and a standard deviation of 1. Okay, this is a definition of something, right? The diagrams below show standard normal distribution curves. They're perfectly standard, normal, symmetrical, everything. Use a table of standard normal curve areas to determine the shaded areas. Okay, you don't have these. So we are going to stop here, okay, because I need to go back to the table to talk about them. Another one, right? It's a beautiful, symmetric, whatever. And the last one. Okay, so we'll do this tomorrow. And your summary. Okay, good work.